Welcome to the Joy of Architecture. Today we're jumping into something foundational, but also something people often mix up in distributed systems. Message brokers versus streaming platforms. Our mission, like always, is to give you, our listener, a clear path, a shortcut really, to getting your head around this critical architectural choice. We've looked at guides, real-world stories from the big names, and even what's coming next. This isn't just tech talk. It's really about the core philosophy of how your services talk to each other, how they handle data. Okay, let's get into it.
Absolutely. It's fascinating, isn't it? Both help with asynchronous communication, sure, but they come from fundamentally different places, different paradigms. And getting that difference right, it's not just theory, it's absolutely crucial if you want to build systems that are, resilient, scalable, and actually maintainable down the line.
Okay, so let's start right there with the basics, the conceptual overview. What exactly is a message broker? I tend to think of it almost like a digital post office for software parts, an intermediary, right? Takes messages from producers, figures out where they go, sends them to consumers.
That post office analogy. Yeah, it worked pretty well. The core idea behind a message broker is usually the queue. Think of it as a temporary holding place, often first in, first out, FIFO. Its main job, task distribution, handling commands. Each message is like a single piece of work. The broker's role is to make sure that work gets delivered reliably to one consumer that can handle it. And then, this is key, it's usually gone once it's processed and acknowledged.
Got once processed. So how does a streaming platform differ? Because, on the surface, they also seem to pass messages around.
Right, and that's where the wires get crossed sometimes. A streaming platform, it's a different beast. It's a distributed system built for, handling continuous flows of data, high volume, real time. But here's the fundamental shift. Instead of a transient queue, the core idea is a durable, append-only, immutable log. When an event or message comes in, it gets added to the end of this log. And crucially, unlike the broker, it stays there. It's not deleted when someone reads it. It sticks around for however long you configure it, so it can be read, and importantly, reread multiple times by totally different applications. This makes the streaming platform more like a system of record for events. It's really focused on data replication, real-time analytics, that kind of thing.
Got it. So both are super important for asynchronous communication, which, let's face it, is the backbone of any modern scalable system. Could you break down their specific roles a bit more?
Sure. Message brokers, they really shine in those traditional messaging scenarios. Think task queuing. You need to offload a long-running job so your API stays snappy, perfect for a broker. Or load leveling, you get a sudden burst of traffic. The broker acts as a buffer, smoothing things out so your back-end services aren't overwhelmed. And definitely reliable command execution. When you absolutely need that process payment or update inventory command to get through reliably in a microservice world, a broker is often the go-to.
Makes sense. And streaming platforms, where do they fit best?
Streaming platforms are the natural home for event-driven architectures, or EDA, where services react to things that have happened, like an order-placed event. They're perfect for broadcasting events. You publish an event to the central log, and any service that cares can subscribe and react completely independently. They power real-time analytics, things like live dashboards tracking user activity or detecting potential fraud the instant it happens. And they're basically essential for event sourcing, using that immutable log of events as the absolute source of truth for your application's state. You can rebuild state just by replaying the log.
This really brings us to that core distinction you mentioned, the queue versus the log.
Yeah.
You're saying this is the thing for an architect to really internalize.
Absolutely. It's the foundational difference. In the queue model, the broker world, you have what are called destructive reads. A consumer grabs a message, processes it, acknowledges it, and poof. It's gone from the queue. Its job is done. It's very work-centric. The goal is ensuring one unit of work gets done by one worker.
But the log model, completely different mindset.
Completely. The log model of a streaming platform uses non-destructive reads. Consumers read events based on their position or offset in the log. But the event itself, it stays right there in the log. Other consumers can read it. The same consumer can even go back and read it again later if needed. Events are persistent and immutable. It's a durable, time-ordered record of facts, so it's very data-centric. And that unlocks powerful things like replaying history to rebuild state, or for debugging, or for training ML models. So yeah, the big question for you, the listener, when you're designing is, am I dealing with a temporary task that needs doing? Or am I recording an immutable fact that might need to be revisited? Answering that really points you in the right direction.
That's a really clear way to put it. Okay, let's ground this theory. How do these differences actually show up in the tools we use day to day? Let's compare some core characteristics head to head.
Sounds good. Let's start with delivery guarantees. This is always a big one. Message brokers often make it, well, simpler to get strong guarantees for individual messages. Think RabbitMQ with its publisher confirms and consumer ACKs, or Amazon SQS FIFO queues, which offer true exactly once processing for a message. They're often optimized for the transactional integrity of single tasks, like making sure that payment happens exactly once.
Okay, simpler for single messages, but streaming platforms.
Yeah.
Getting exactly once. Semantics, EOS, that sounds trickier.
It is, definitely. Streaming platforms usually give you at least once delivery out of the box. Getting to exactly once semantics is a much heavier lift. It's not just about the platform. It's an end-to-end system concern. You need things like idempotent producers, maybe transactional processing within your consumer application, and atomic commits across producing and consuming. Kafka, for instance, has its transactions API, which is powerful, but frankly adds significant complexity to your application code to get EOS right.
Right. Okay, moving on to message retention and replayability. You hinted at this, but this feels like the game changer architecturally.
I think it really is. Message brokers typically offer transient storage. Messages are meant to be consumed and then deleted. Replaying isn't really a built-in feature. You'd have to architect that yourself, maybe by archiving messages elsewhere and republishing. Streaming platforms. They're fundamentally built on durable storage. Replayability isn't an add-on, it's a core capability. Events stick around for days, weeks, even indefinitely, depending on your configuration, regardless of who has read them. And that ability unlocks so much. Event sourcing, like we mentioned, rebuilding state from scratch, onboarding a brand new service that needs historical context without a massive, complex backfill process. Feeding historical data to analytics or ML pipelines, huge.
Huge difference indeed.
Yeah.
What about message ordering and partitioning? How do they handle keeping things in sequence?
Good question. With message brokers, you usually get strict FIFO order within a single queue. But often, that only holds if you have just one consumer pulling from that queue. If you add more consumers to scale out processing, what we call competing consumers, you typically lose that strict end-to-end ordering across all messages. Streaming platforms guarantee strict FIFO order, but crucially, it's per partition. There isn't a single global order across all partitions in a topic. So if you need related events processed in order, like all updates for a specific customer, the producer needs to be smart and use a partition key, say the customer ID, to ensure all those related events land in the same partition. That partition then guarantees order, and you can scale horizontally by adding more partitions for other keys.
Okay, so ordering is tied to partitioning in streams. How about how consumers actually get the messages, the consumer models?
Yeah, that differs quite a bit too. It often comes down to push versus pull. Message brokers frequently use a push model, or maybe a smart pull, where the broker actively sends messages out to available consumers. You see competing consumers pulling work off a queue, effectively load balancing, or you might have a publish-subscribe setup using exchanges or topics where the broker pushes messages to all subscribers. Great for distributing distinct tasks. Streaming platforms almost always use a pull model. Consumers are in charge. They connect to the broker and ask for data starting from a specific offset in the log. They control the pace. And the key concept here is the consumer group. Multiple applications, each represented by a consumer group, can read the entire stream of data independently, keeping track of their own position, offset. This lets you have, say, a real-time analytics system, an auditing system, and a notification system, all reading from the same event stream without stepping on each other's toes.
That independent consumption is powerful. Now, the big one for many systems, scalability and throughput. How do they stack up?
Message brokers typically offer, let's say, moderate throughput. Scaling them up, especially while trying to maintain guarantees or ordering, can get complicated. Streaming platforms, on the other hand, are built for very high throughput. Think hundreds of thousands, even millions of messages per second. They achieve this through horizontal scaling. You need more capacity. You just add more broker nodes to the cluster and potentially more partitions to your topics. It's inherently designed for massive scale.
Okay, but that scale often comes with a cost, right? What about operational complexity and observability? That's a huge factor for any architect listening.
It absolutely is. Generally speaking, message brokers tend to be simpler to deploy and manage, especially for basic use cases. And managed services like Amazon SQS or Azure Service Bus, they make the operational burden almost disappear. That's a massive advantage, especially in serverless or lean environments, running something like Apache Kafka yourself. Historically, it's been more complex, managing the cluster, dealing with dependencies like Zookeeper, though craft mode is simplifying that, now it requires expertise. This complexity is a big reason why managed streaming services like Confluent Cloud, AWS MSK, or Google PubSub are so popular. In terms of observability for streams, a key metric you're always watching is consumer lag, how far behind the latest data a particular consumer group is. Keeping that low is critical for real-time applications.
Makes sense. And lastly, in this comparison, fault tolerance and high availability, HA.
Both can definitely be made highly available, but they do it differently. Message brokers typically rely on clustering, persisting messages to disk, and specific features like mirrored queues or quorum queues in RabbitMQ. Streaming platforms, particularly Kafka and Pulsar, have HA baked into their core design via partition replication. Each partition has a leader and multiple followers spread across different brokers, often in different physical locations or availability zones. If a leader node fails, one of the followers is automatically elected as the new leader, usually within seconds, ensuring data keeps flowing with minimal disruption. But again, the sophisticated HA comes with that operational overhead if you're running it yourself. So it comes back to that question for you, the listener. What level of operational effort are you prepared to invest to get the scale and resilience you need?
That's a fantastic breakdown of the core differences. Okay, so knowing all that, how does it translate into actual system design? Let's talk design patterns and use cases. Where does each technology really fit?
Right. For real-time data pipelines moving large volumes of data, continuously streaming platforms are hands down the better choice. Their throughput, durable buffering, it's what they're built for. Think Kafka, Kinesis, Pulsar here. Brokers just don't handle that kind of sustained volume well.
Okay, clear win for streams there. What about event sourcing and CQRS, command query responsibility segregation?
For event sourcing, again, streaming platforms are the natural fit, that immutable, replayable log. It is the event store. It's the perfect physical implementation for recording every state change as an event, providing that single source of truth, message brokers. Not suited for event sourcing itself because they lack that persistent, replayable log. However, brokers can absolutely be used effectively in a CQRS architecture without event sourcing. You might use a broker queue to reliably deliver commands to the right side of your system, or use a broker topic to publish integration events to update the read side. They work well for the communication aspects of CQRS.
Interesting distinction. What about complex workflow orchestration, like managing a multi-step business process?
Here, message brokers often have the edge. Especially tools like RabbitMQ or Azure Service Bus. They often have more sophisticated routing capabilities, support for patterns like request reply, scheduled messages, or managing Saga patterns for long-running transactions. They're generally better suited for managing the control flow of a business process. Streaming platforms, less ideal for direct business process orchestration. Their focus is more on the continuous flow of data, not so much on coordinating complex, stateful steps.
Right. What about IoT data ingestion? That feels like it could go either way, with potentially huge volumes, but also maybe needing reliable delivery of specific commands.
It's often a hybrid scenario, actually. For the central aggregation point where all the data lands, streaming platforms are usually preferred because of the potentially massive throughput needed. But at the edge, closer to the devices, you often see lightweight message brokers using protocols like MQTT or NATs. They're efficient, handle intermittent connectivity well, and can act as local aggregators before forwarding data in bulk to the central streaming platform. So often a mix and match approach.
Okay, hybrid makes sense there. How about simple command handling and microservices? Just telling another service do this.
For that specific pattern, message brokers are typically an excellent fit. You want reliable, often point-to-point delivery of a command. Competing consumers on a queue give you easy scaling. And the transient nature of a queue matches the use case. Once the command is done, you don't need a permanent record of it in the message system itself. Using a durable, replayable log like Kafka for simple, ephemeral commands can be overkill, an anti-pattern, really. It adds complexity without much benefit for that specific job.
Gotcha. And finally, log processing and analytics, collecting logs from everywhere.
Oh, streaming platforms dominate here. It's one of the original killer use cases for Kafka, developed at LinkedIn precisely for this. A streaming platform acts like a massive distributed pipe that can just absorb the fire hose of logs coming from all your applications and infrastructure. That durable log then allows multiple downstream systems to consume the logs independently. Maybe one system for indexing and search, like Elasticsearch, another for long-term archiving, another for real-time anomaly detection. Brokers just can't handle the volume or provide the durable, multi-consumer access needed.
Okay, the patterns make the choice clearer. Now let's quickly touch on the specific tools people might encounter, the technology landscape.
Sure. For message brokers, some big names are RabbitMQ, very flexible routing with AMQP exchanges, great for complex scenarios needing precise delivery, strong per message guarantees, maybe lower raw throughput than top streaming platforms, but very mature and reliable. Amazon SQS. Fully managed, super simple, scales massively. You've got standard queues for at least once, best effort order, and FIFO queues for exactly once, stripped order. Deep AWS integration, but less routing flexibility and, well, it's AWS specific. Azure Service Bus, Microsoft's equivalent in Azure. Enterprise-grade queues and topics, lots of features like dead lettering sessions, transactions, great fit if you're in the Azure ecosystem. NATS, known for being incredibly fast, low latency, and simple. Core NATS is at most once. Jetstream adds persistence and streaming capabilities, kind of bridging the gap, popular in edge computing and high-performance scenarios.
Good overview. And the key streaming platforms.
The main ones you'll hear about are Apache Kafka, the 800-pound gorilla. It's the de facto standard. Extreme throughput, distributed, partitioned, replicated log. Huge ecosystem with Kafka Connect, Kafka Streams, powers massive companies. Main consideration, as we said, is operational complexity if you run it yourself. Apache Pulsar, often seen as the next-gen cloud-native alternative. Its big architectural difference is separating compute brokers and storage using Apache Bookkeeper. This allows independent scaling, easier multi-tenancy, built-in geo-replication, maybe a bit more complex architecturally overall, but very flexible. Red Panda, a newer player, aiming to be Kafka compatible but faster and simpler. Written in C++, single binary, no zookeeper craft dependency needed, claims much lower tail latencies and better resource efficiency. Gaining traction quickly, Amazon Kinesis, AWS's fully managed streaming suite. Data Streams is the core offering, using shards for scaling. Provides managed scaling at least once guarantees, strict order per shard, very convenient for AWS-centric real-time analytics pipelines. Google Cloud PubSub, Google's managed service. It's interesting because it's kind of a hybrid, acts like a bunker, but also has message retention and replay, giving it streaming-like capabilities for multiple subscribers. Global scale integrates tightly with GCP.
That's a lot of choice. Any quick thoughts on performance benchmarks? It always comes up, Kafka versus X.
It does, and benchmarks can be tricky, highly workload dependent. But general observations, Kafka usually demonstrates higher sustained throughput than RabbitMQ due to its log structure and sequential I/O optimizations. RabbitMQ might edge out on latency for very small, individual messages at lower volumes, but Kafka scales better under load. RabbitMQ Streams is their answer to compete on throughput. Pulsar versus Kafka is hotly debated. Pulsar often claims better tail latency, consistency at the high end, because of its architecture. Kafka proponents often point to higher raw throughput in many benchmarks. It really depends on your specific workload and tuning. Red Panda versus Kafka. Red Panda's pitch is significantly lower tail latencies and better CPU memory efficiency thanks to C+++E. Independent tests often show Kafka might still achieve higher absolute throughput on some hardware or workloads, but Red Panda's efficiency is compelling. Kinesis versus Kafka. Kinesis offers predictable, managed performance based on the number of shards you provision. Easy to scale up and down. A well-tuned, self-hosted Kafka cluster can often achieve higher throughput than Kinesis, but requires that operational effort. Kinesis can be cost-effective for variable loads. Kafka might be cheaper at massive, constant scale if self-hosted.
Okay, super helpful context. Let's make this even more concrete. How have major companies used these in real-world case studies?
Great idea. Let's look at Netflix's Keystone pipeline. They faced a huge challenge, unifying data ingestion from thousands of microservices and millions of devices, replacing tons of different specialized systems, trillions of events per day, their solution. They built Keystone around Apache Kafka as the core data transport layer. Kafka provided that massive durable buffer they needed. They paired it with Apache Flink for real-time processing on those streams. Why Kafka? They needed a universal data pipeline, a central nervous system. Kafka's extreme throughput, its durability and replayability, allowing many different teams and systems to tap into the same data independently was key. It fundamentally shifted their thinking from point-to-point service communication to providing unified data access for the entire organization.
A classic example of the data backbone pattern. What about Uber? They had an interesting evolution, right?
They did. Uber runs one of the largest Kafka installations anywhere. But they ran into trouble when they tried using Kafka directly for asynchronous task queuing for some microservices. They hit that head-of-line blocking issue we discussed. A single slow or problematic message in a Kafka partition could hold up processing for all subsequent messages for that service instance. Not ideal for task work where you want parallel processing. So their clever solution was to build an abstraction layer they called a consumer proxy on top of Kafka. This proxy consumes large batches from Kafka partitions efficiently, but then it dispatches individual messages to the actual service instances in parallel, managing acknowledgments per message.
Ah, so they kept Kafka's scale but layered queue semantics on top.
Exactly. They got the best of both worlds. Kafka's underlying scale, durability, and ecosystem, but with the semantics they needed for task queuing parallel processing, isolation from poison pill messages, no head-of-line blocking at the service level. It's a brilliant example of adapting the tool and recognizing when a pure streaming model wasn't the perfect fit for every async task. And interestingly, this pattern is now becoming a first-class feature in Kafka itself with Kippy 932 share groups.
Fascinating. And we can't talk Kafka without mentioning its origin.
LinkedIn, right, the birthplace. LinkedIn's problem was the opposite of Netflix's initial state. In some ways, they had too many specialized point-to-point data pipelines. It was becoming an operational nightmare to manage all these different systems. So they created Kafka specifically to be a single, centralized, distributed, publish-subscribe platform to unify all data flows across the company. The core design goals were horizontal scalability via partitioning, providing a unified data source that both real-time online systems and offline batch systems could consume, and high performance. It really drove that strategic shift towards treating data infrastructure as a central platform, not just an application concern. It also showed the significant investment needed to operate such a platform at scale, leading them to build tools like cruise control for cluster management.
Okay, incredible insights from the trenches. So let's bring this all home. For the architect listening, making the choice, what are the key architectural trade-offs, and how do we build a decision matrix in our heads?
The absolute first question goes back to that core paradigm. Broker-based versus log-based. Choose a broker-based queue system when your main goal is passive distribution. You're handling discrete work units. The message is essentially an ephemeral command, do this thing, then forget the message. Replay isn't needed. You want to reliably execute commands or distribute jobs across workers. Choose a log-based stream system when your main goal is data replication and processing continuous event streams. The event is an immutable fact that needs to be stored durably. You need replayability. Multiple different applications need to consume the same data history independently. It's about creating a system of record for events.
And how do performance trade-offs fit into that decision? Throughput versus latency.
Right. For sheer throughput, moving massive data volumes, streaming platforms are generally the winners. For latency, it's nuanced. For single, small messages, especially at lower volumes, a lightweight message broker might offer slightly lower end-to-end latency. But streaming platforms are designed to maintain consistently low latency, even at very high throughput, which brokers might struggle with.
What about the data access patterns? Replayability is obviously huge.
Replayability is the killer feature for log-based streaming. If you anticipate any need to reprocess historical data, maybe to fix a bug and rebuild state, train a new ML model, or onboard a new service that needs history, you need a streaming platform. Brokers just don't offer this natively. For real-time responsiveness, specifically for transactional point-to-point interactions involving those ephemeral commands we talked about, brokers often provide simpler interaction models and potentially better responsiveness for that specific task as you avoid the overhead of the durable log.
And finally, the practicalities. Operational and financial considerations. Cost, cloud-native fit.
Big factors. Cost. Managed services like SQS, Kinesis, or PubSub can be very cost-effective, especially for bursty or moderate workloads because you pay for what you use and offload the operational burden. Self-hosting Kafka or Pulsar can be cheaper at very large, sustained scales, but you have to factor in the significant operational costs, the engineers, the tooling, the infrastructure management, for cloud-native compatibility. Managed services are obviously deeply integrated with their respective clouds. Architecturally, platforms like Pulsar, with its compute storage separation, and Red Panda, single binary, no external dependencies, are often highlighted as being particularly well-suited for elastic scaling in cloud or Kubernetes environments.
This field isn't standing still, though. What are the future trends and evolutions we should be watching in asynchronous messaging?
Yeah, definitely evolving. A major trend is what I'd call the great convergence, unifying queues and streams. For years, you often needed separate clusters, a broker for tasks, a streaming platform for data pipelines. That two-cluster problem is starting to blur. We're seeing streaming platforms adding queue semantics. We mentioned Kafka's upcoming share groups, CAPI 932, for load balance consumption. Pulsar already has flexible subscription modes allowing shared queue-like or exclusive stream-like consumption on the same topic. And conversely, message brokers are adding stream semantics. RabbitMQ Streams, for example, is basically an append-only replicated log built into RabbitMQ to compete directly on high-throughput use cases. The implication here is potentially simpler tech stacks in the future. You might choose the pattern you need, queue or stream, without necessarily deploying to entirely different platforms.
That's a big shift. What about serverless?
Absolutely. The rise of serverless messaging and event buses is huge. We're moving away from needing long-running consumer applications for everything. Instead, you have stateless functions triggered directly by events. The messaging system increasingly acts as a central event bus. Think Amazon Event Bridge, Azure Event Grid, Google Event Arc. These services are less about raw streaming throughput and more about intelligent routing, filtering, and reliably triggering functions or other services based on event content. This drastically reduces operational overhead. You focus on the business logic in your function, and the cloud provider handles scaling the event delivery fabric. It strongly favors these managed integrated cloud services.
And making all these different systems talk to each other. Standardization must be key.
Exactly. That brings us to cloud events. The historical problem was every platform, every service emitted events in its own proprietary format. Integrating them was a pain. Cloud Events is a CNCF specification that tackles this. It defines a standard envelope, a common set of metadata attributes like event ID, source, type, timestamp that wraps the actual domain-specific event data, the payload. It doesn't standardize the payload itself, but the metadata envelope. The impact is potentially huge, real interoperability. You can build generic tooling for routing, filtering, security, and observability that works across different event sources and platforms because they all share the same metadata structure. It helps future-proof your architecture. Major clouds and projects are adopting it rapidly. If you connect the dots, the trend seems to be towards this unified, smarter, standardized event fabric. Converged platforms that can handle both queue and stream patterns, speaking cloud events, triggering serverless compute seamlessly. So wrapping it all up for you, the senior architect listening, this choice, broker versus stream, it's not just a feature checklist. It really comes down to those two fundamental paradigms we keep hitting on. Are you managing work or are you managing data?
Right. So let's summarize the recommendations concisely. You should probably choose a message broker when your primary goal is task-oriented communication. Think commands, jobs, tasks. The message itself is ephemeral. Its value is in getting the task done, and that's gone. Replay isn't a requirement. It's perfect for distributing workload across identical workers, handling background processing, or maybe orchestrating complex workflows needing specific delivery guarantees for each step.
Exactly. And you choose a streaming platform when your main focus is data-oriented communication and building that durable system of record. Think events, streams, source of truth. The data must be durable. It must be replayable for potential future use cases like analytics, state reconstruction, or auditing. You need multiple different kinds of applications to consume the same data independently. And you often need strict ordering of related events managed via partitioning at massive scale. Think real-time pipelines, event sourcing, central log aggregation.
But as the Uber example showed, it's not always strictly one or the other, right? Hybrid systems are common.
Very common, especially in complex systems. You might use a broker for commands and a stream for events. Get the best of both worlds. Reliable task execution from the broker and a durable, auditable event log from the stream. Or use the stream as a universal ingestion layer like Netflix. All raw data and events flow into the central streaming platform first. Then, maybe specific actionable tasks derived from those events get pushed onto broker queues for reliable processing by worker services, similar in spirit to Uber's consumer proxy pattern. It always comes back to asking yourself that fundamental question for each piece of data flowing through your system. Is this an instruction to be executed once and then forgotten? Or is this a fact, an event that happened which needs to be recorded durably and might be needed again later?
That clarity, that distinction is probably the most valuable tool you have for building the truly scalable, resilient, and increasingly data-driven systems we need today and tomorrow. Thank you so much for diving deep with us on this today. It's been incredibly insightful. And for everyone listening, don't forget to subscribe to Joy of Architecture so you catch our next deep dive.